In this video, I'm going to be covering how to do voltage drop calculations according to the Canadian Electrical Code for any AC circuits. So the first thing we got to do is take a look at some assumptions that we're going to be looking at. Any calculation we're going to do in this video will be based upon an assumption that the equipment involved is rated for 75 degrees for a termination temperature rating. We're also going to be assuming that any time we're looking at a conductor arrangement, it would be installed in a raceway or it would be a cable assembly. So now that we've taken a look at those assumptions, let's get started by taking a look at the base rule that's going to be guiding this process. In 8102, we're given our base rule for voltage drop, and we're told that no branch circuit or feeder shall have more than a 3% voltage drop on the conductors. Another way of looking at that is saying that the minimum voltage available at the load would have to be 97% of the source voltage. So that's kind of the inverse of the voltage drop rule. Now, in order to make sure that we abide by this and that we have a sufficiently high voltage at the actual load that's being served, we need to size our conductors accordingly. When we do our calculations, it's very important that we base our calculations on either the known load ampacity or on 80% of the overcurrent device rating. And so if it's a 15 amp breaker and we actually don't know how much current the specified load will draw, we would have to base it on an ampacity for the load of 12 amps, 80% of 15. So now when we move forward, we'll be using this maximum voltage drop allowable of 3% anytime a question does not have a specific limitation on voltage drop. Now let's take a look at the factors that are involved in causing voltage drop on the conductors themselves. At the end of the day, when we look down at the circuit level, we have to recognize that whether it's a copper conductor or an aluminum conductor, those conductors will have inherent resistance of their own. Now we know that copper and aluminum are very good conductors. They have a relatively low resistivity. However, the resistivity of the material itself does naturally cause our conductors to end up with a voltage drop across themselves because they end up acting like a series load within the circuit. And so we'll often represent this by showing a small series connected resistor with whatever load we're looking at. And those small series connected resistors are given as representing the overall resistance of the circuit itself, the conductors themselves, and it gives us a way of just illustrating the fact that we will end up with a certain number of volts of voltage drop on these lines. And it's that we're concerned about, because ultimately if we are losing 10 volts on this given circuit, let's assume that the circuit derives from a 120 volt source. If we are in fact losing 10 volts on this circuit, just on the conductors, then that will only leave 110 volts for the load. And at 110 volts on a 120 volt circuit, that represents only 92% of what it should be, 120. And therefore we're looking at an 8% voltage drop on this scenario. Now the consequence of this, why this is so important, is that ultimately if we consider the fact that the power output of a load, assuming that the resistance or the impedance of the load stays constant, then the power output will always be proportionate to the square of voltage. And that means that a drop in voltage has a significant effect in dropping the power output capacity of the load. For example, this 8% voltage drop here would result in an equivalent power drop of around 15.36%. And so the reality is that when voltage drop occurs on the conductors that feed loads, that ultimately causes a significant change in the power dynamic that load is able to produce. And so our loads, whether they're baseboard heaters or motors or light bulbs, will not actually put out their rated power if they are under voltage. And so when we take a look then at the factors that are involved in causing voltage drop on the conductors, we recognize that the reason for it is the inherent resistance of the conductors themselves. And there's a number of factors that come into play in determining that resistance. And so here I'm showing a formula for how we would calculate the resistance of a conductor. And ultimately it's based upon what the conductor actually is made out of. So is it a copper conductor or is it an aluminum conductor? And this K factor it's a constant for each of those material types, and it's a resistivity constant. And so for copper it is 10.4, and for aluminum it's 17. So aluminum actually has a resistivity that is approximately 63.5% greater than that of copper, which means that for two conductors of the same CMA, one being aluminum and one being copper, the aluminum one would have around 63.5% greater resistance per unit length than the copper one. Now beyond the material itself, the resistance of any conductor is also going to be based upon the length of that conductor. And as can be seen from the formula, the length of the conductor has a direct relationship with the resistance. In other words, as the length of the conductor is increased, the resistance of that pathway also increases. Now the last factor that has a significant impact on the resistance of the circuit pathway is the actual AWG gauge of the conductor, or rather the cross-sectional area of the conductor. And based on the American wire gauge system, we refer to the cross-sectional area of the conductor by the unit CMA. And CMA is calculated for any conductor by taking the diameter squared, and that diameter would be in mils, a mil being 1/1000th of an inch. So it's a very unique sizing system, but it is the one that we use. So when we now look at the additional factor that impacts the resistance of a circuit, it is the temperature of the conductors. And frankly, it's a relatively low effect compared to the material of the conductor, the length of the conductor, and the CMA of the conductor. But the temperature does come into play. And so once again, we can see that temperature has a direct impact on the resistance of the circuit. And so as the temperature of the material increases, so the resistance of the material will also increase. Now again, this is based upon a constant that is related to the type of material it is. And so we have, for copper, a temperature coefficient of 0.00393, and for aluminum, a temperature coefficient of 0.0039. Which means that, essentially, you can predict an increase of approximately 0.039 of an ohm per degree Celsius increase per ohm of original resistance. Now that that's all cleared away, let's go and just summarize the factors that impact the resistance of a circuit. First off, the material that the circuit actually is made out of. In other words, are the conductors copper or are they aluminum? Also, how long is the circuit? The longer the circuit, the greater the resistance of that circuit. And then, lastly, what is the AWG gauge of the wire itself? If it is a larger AWG gauge, then the resistance of that circuit for a given length and a given type of material will be lower than one where the AW gauge is a smaller gauge. Then in addition, the temperature of the installation comes into play. Where the conductors are operating at a higher temperature, they will naturally have a higher resistance. So if these are the factors that impact the resistance of a circuit, then there must be an additional factor within the circuit that ultimately impacts the amount of voltage drop in the circuit. Because at the end of the day, thinking about Ohm's law, voltage is always equal to the combined interaction of the amount of current in the circuit and the amount of opposition to that current in the circuit. And so therefore, when we consider the voltage drop on the conductors, we must always consider two things. The resistance of the actual conductors themselves must be considered, but in addition to that, the amount of load current will also have a significant impact on our voltage drop calculations. So when we now start considering how to do a voltage drop calculation according to the CEC, we're going to be looking at both of these factors. The resistance of the conductors themselves are going to have an impact, and of course the load current itself will have a significant impact too. So let's get started on how to calculate voltage drop according to the CEC. The fundamental basis for a voltage drop calculation is going to be the values that we get out of table D3 and the last kind of concluding section of table D3, which deals with distance correction factors. In addition to those values that we get from table D3 and table D3 concluded, we're also going to be using a number of circuit characteristics and code limitations on voltage drop in determining the maximum distance that we can actually have a load placed away from the source of the circuit that feeds it. When we get started here, we have to understand that the direction that the code comes at the problem from is the direction of setting a limitation on the maximum distance that we can go from the panel or fusible disconnect or whatever it is that's feeding the branch circuit or the feeder out to the load. So one way of thinking about it is that this would be a limitation on the maximum length of cable that we could install between those 2 points, between the source of the branch circuit and the load that the branch circuit supplies. Now when we take a look at the factors that are going to be involved in that calculation, the first and foremost is a value that we would get out of table D3. And this is a value in meters. So for example, it might be a value of 6.2 meters. And this is the maximum distance that we could go based on a 1% voltage drop and a 120 volt circuit. Then what we have to do is we have to actually look at the circuit characteristics that we will have, and therefore we need to look at the voltage of the circuit we would actually be calculating, because table D3 being based on a 120 volt circuit does not automatically then account for a 240 volt circuit or a 277 volt circuit, for example. So we must have some form of voltage multiplier, because if we have a larger voltage source for the circuit than 120 volts, then we would naturally be allowed to go further for the same percentage voltage drop. And therefore our voltage multiplier will always be based upon our actual circuit voltage divided by 120, which is what the table is based upon. Then we also need to account for the fact that the table is only based on a 1% voltage drop. And we know that our actual permissible voltage drop, based on a standard code value, is 3%. Which means that in reality, we can actually go 3 times further, according to code, than this base number out of table D3. So therefore, we need a voltage drop multiplier as well. And this will be based upon our circuit maximum voltage drop divided by 1. If there is no specified maximum voltage drop, then we would go based upon the maximum voltage drop permissible by code, which is 3. However, it's quite possible that a question or a specification may actually limit us to a 2% voltage drop, and therefore it would become a 2 divided by 1 voltage drop multiplier, or simply a multiplier of 2. Now the last value in this chain is our distance correction factor, and the distance correction factor is taken from table D3 concluded, and it's based upon a couple of different factors. One is the percentage loading of the circuit, and so we know that each AWG size of conductor for copper and for aluminum has a maximum allowable ampacity, and now our actual load ampacity will be compared to the maximum allowable ampacity for the conductor size we're dealing with to determine a percentage loading on that conductor. The greater the percentage loading, the less of a multiplier we will get from our DCF, or distance correction factor. The other thing that the DCF is based upon is the actual temperature rating of the conductors themselves. And so we'll take a look at how that breaks down when we do an example. But just to reiterate, what is the D3 value? Well, it's based on conductor size, and the conductor size is used to determine the column of table D3 to use, and it's also based upon the load ampacity, that is how much current our load is actually drawing, and that would be the row within table D3. So when we go into table D3, we have to come at it from the perspective of having these two pieces of information already for a standard voltage drop calculation. So we would have to know, for example, that we have a 10 amp draw on the circuit. We would also need to know that we plan to run number 10 AWG wire, for example. Using those two values that we know, we can go into table D3 and we can use our 10 amps as our row, number 10 AWG as our column, and go down to the intersection of those two and get a value of 15.5 meters to begin our calculation with. Now again, I want to reiterate that this is the maximum distance that the load could be from the circuit origin for that amount of current on that wire size, but it's based on two key limitations or constraints. The table is based upon a 1% voltage drop and a circuit voltage of 120 volts. So, as I mentioned already, we will need multipliers to go ahead and adapt this to the specific circuit characteristics that we're dealing with. How do we modify this base D3 value? Well, it's going to be multiplied by some form of voltage multiplier, and also the amount of permissible voltage drop that we are actually allowed. And so when we now take a look at the fact that this number 10 AWG conductor carrying 10 amps may actually be connected to a 240 volt circuit, we can actually go twice the distance for the same amount of voltage drop, or the same percentage of voltage drop. And therefore we need a multiplier of times 2. And once again, this is based upon your actual circuit voltage compared to the 120 that table D3 is based upon. So now we have our voltage multiplier. Likewise, we go and take a look at our maximum voltage drop permissible. And if the question or the real-world scenario does not specify anything different, then we can go based upon the maximum laid out in Rule 8102, and that is 3%. And so this means that we can actually go 3 times further than the value straight out of D3, because that value is only based on a 1% voltage drop. We're allowed 3%, and so we end up with a multiplier of times 3. Now the last factor, our DCF, is a little bit more complicated, requires a little bit more work from our perspective. It's also going to be a multiplier, but as I mentioned already, it's based upon the loading of the conductor that we're using relative to its maximum allowable ampacity and the insulation temperature rating of the conductor. And again, it's taken from table D3 concluded. So in order to do our calculation for the loading of the conductor, we are going to need 2 things. We're going to need to know our load ampacity, which we're given as 10 amps, and then we would also need to go and take a value out of the appropriate ampacity table for the given wire size, and that is the maximum conductor ampacity. So for example, what we would do is we would go to table 2, assuming that we are running copper conductors up to this point, and we would use our number 10 AWG that we've been looking at so far and go across at number 10, and then we would take our maximum ampacity from the 75 degree column, because we're working in this video from the assumption of a 75 degree termination temperature. So even if we were running R90, we would still use the 75 degree column. And what you would see there is that we are allowed a maximum of 35 amps worth of current on these number 10 conductors. Now what we have to do is compare our actual load ampacity of 10 amps to this maximum allowable of 35 amps, and we end up with a value of around 29%. From that point, now that we have a percentage loading value, we can go to table D3 concluded, and using, for example, as we said, RW90 as our conductor type, that means that we would have a 90 degree insulation temperature rating to use in table D3 concluded, meaning that we would go across the table at the 90 degree C row until it intersects with a percentage column that is equal to or greater than our percentage loading that we just calculated. And so we just calculated a value of around 29% loading. The lowest column available to us in table D3 concluded is 40%, and so that is the table that we, or rather the column that we have to select. So we go down the 40% column, and our multiplier for our DCF would be 1.08. This can now be used to modify our base distance in addition to the voltage multiplier and the voltage drop multiplier. And so ultimately, what we should end up with from our example thus far is a scenario whereby we got 15.5 meters out of table D3. We then get a times 2 multiplier for voltage, a times 3 multiplier for our voltage drop, and a times 1.08 multiplier for our DCF. And this gives us a grand total distance that we can run our number 10 conductors, feeding 10 amps at 240 volts of 100.44 meters. Now let's go ahead and put all of these steps together in one full example. So we're going to take a look at an example where we have a 240 volt circuit, just like we've been looking at. We're running number 10 R90 copper, and we want to know what is the maximum distance that we can have between the load that draws 21 amps and the panel that supplies it. So the first thing we have to do is we have to go to table D3 and get our D3 value. To do that, we use our current and our wire size from the question. Now when we go to table D3, we'll notice that there is no option for 21 amps. And therefore, what we must always do is go to the next available higher current that is in the table. That means that when I actually do my calculation in table D3, I would select 25 amps as my current and go across at that row. The intersection at number 10 AWG gives us a D3 value of 6.2 meters. That is my base number that I'm going to now multiply with a voltage multiplier based on the fact that my circuit is 240 volts, whereas the actual table is only based on 120. So I'm able to go twice as far as the table is telling me. So I take my 240 divided by 120 and I get my times 2 multiplier. I now need to go and get a voltage drop multiplier. Because the question has not specifically addressed a percentage voltage drop, in other words, it hasn't put a different limitation on this installation than the base code limitation, then I'll take the base code limitation, which is 3%. And therefore I get a multiplier for my circuit of times 3. In other words, I can go 3 times the distance that table D3 gave me. The last step is to calculate my DCF. And again, this is a little bit more complicated because it requires us to go back to table 2 and get our actual ampacity allowable for the number 10 wire. But when I do my calculation, I take my actual load ampacity of 21 amps, I divide that by the allowable maximum ampacity of the number 10, which is from table 2. That gives me a loading of 60%. I now take that 60% loading into my table D3 concluded, and I go to the 60% column. I'm running R90, and therefore I use the 90° C row, and that gives me a distance correction factor of 1.04. Now what I have is my D3 value, I have a voltage multiplier, I have a voltage drop multiplier, and I've just calculated a DCF for this problem. All that's left to do is go ahead and actually do the calculation with each of these multipliers. And so I take my 6.2 from table D3, I multiply it by my voltage drop multiplier and my voltage multiplier respectively, and then I also multiply it by my DCF, and I end up with a grand total distance that I can have between my load and my panel of 38.68 meters. And as mentioned before, another way of thinking about this is that this number now represents the maximum length of cable that I could run between the panel and the load, for example. So now that we've taken a look at the whole process, let's do another example. This time we're going to be looking at a 347 volt circuit we're going to be looking at a circuit where we're going to run number 12 AC90 copper, and we want to know what the maximum distance is between the load, which draws 12 amps, and the panel that supplies it. And in this particular problem, we are given a specific limitation of 2% voltage drop in the question. So we can no longer use the 3% allowable by code. We've actually been told that we're allowed a maximum of 2%. So now our first step, as per usual, is to go to table D3 and get our D3 value. To do that, we need to use the 12.5 amp row. Again, the table does not have a 12 amp row, and so we must go to the next available higher ampacity. And therefore we go to 12.5 amps. We go across the table at that row until it intersects with our wire size, and that is number 12 AWG. There we get a D3 value of 7.8 meters. Now we need to find out our multipliers for this base value, starting with our voltage multiplier. And in this case, what we do is we compare our 347 volt circuit with the 120 volts that table D3 is based upon, and we get a multiplier of 2.8916 repeating. Then we go and get our voltage drop multiplier. As mentioned already, the question does in fact specify a maximum of 2% voltage drop, and so in this case our voltage drop multiplier is only times 2. Lastly, we need to go and get our DCF value, and to do that we're going to have to first calculate our percentage loading. And so we take our actual load amps of 12 amps and we compare that to the 25 amps maximum ampacity out of table 2. Again, we're running number 12 AC90 copper, and so we would be getting our ampacity for these conductors out of table 2. We'd be using the 75-degree column because this video is based around the assumption that all of the equipment would be termination temperature rated for 75 degrees. And so when I compare my 12 amps to my maximum allowable of 25 amps on the number 12, I get 48% loading. When I now go to table D3 concluded, there is no 48% column, and so therefore I must go up to the next available higher percentage. And that takes me up to 50%. Now once again, because I'm running AC90, I use the 90-degree C row, and that gives me a DCF of 1.06 out of table D3 concluded. Now that I have my D3 value, my voltage multiplier, my voltage drop multiplier, and my DCF, I simply need to do the calculation. And so I take my 7.8 from table D3, multiply it by my 2.891666 repeating. That is my voltage multiplier. I also multiply it by my voltage drop multiplier of 2 and my DCF of 1.06, and I get a grand total distance between the panel and the load of 47.8 meters. And again, another way of thinking of this is that this is the maximum length of AC90 cable that I could use to run between the panel and the load. Now let's take a look at one last example, and that is one where we're going to be using aluminum conductors. And before we actually start tackling the problem, I just want to point out how we deal with the issue of the aluminum conductor, because table D3 is based upon copper conductors. So, in note 5 of table D3, we see that aluminum conductors need to be treated as though they have a similar conductivity to a copper conductor that is 2 AWG sizes smaller. Now the implication of that is that when we are going into table D3 to select a D3 value, what we have to do is we have to do this based upon a conductor that is actually 2 AWG sizes smaller than the one that we are dealing with for the aluminum. So now let's take a look at actually how to do this. Let's take a look at an example where we're still doing a 240 volt load. Here the load draws 32 amps worth of current. And the question is now, what is the maximum distance or maximum length of cable that can be used to supply the load if we're using 3 conductor number 6 ACWU? So because of the fact that our number 6 ACWU would have an equivalent conductivity to a number 8 copper conductor, Tech 90 for example, then we need to actually use number 8 within table D3, not number 6. So what we have to do then is we go into table D3, we use our actual load current of 32 amps from our question, and we go across at that row until we intersect with number 8 AWG, which is 2 sizes smaller than our actual aluminum conductor. And we get that D3 value of 7.7 meters. Now we can carry on with the rest of the calculation as we would previously. So we need to get a voltage multiplier. Here we have a 240 volt circuit. Of course, table D3 is based on 120 volts, and so we end up with a voltage multiplier of times 2. We then proceed to get our voltage drop multiplier, and because the question does not actually specify any kind of voltage drop limitation, we will go based upon the maximum voltage drop allowable by code, and that is our 3%, giving us a voltage drop multiplier of 3 times. So now that we have our D3 value, our voltage multiplier, and our voltage drop multiplier, all that's left to get is our DCF. And this is where it gets a little bit tricky when we're dealing with our aluminum conductor. We used a copper conductor that was 2 sizes smaller when we were dealing with table D3. However, the reality is that the conductor we are running is in fact aluminum. So when we do our calculation for a percentage loading, we need to do this based upon the actual conductor that we are running, not the hypothetical conductor we used in table D3. So when we do our percentage loading, we actually do need to base it upon the allowable ampacity of the number 6 ACWU. So we go to table 4 for aluminum, and we see that our number 6 ACWU, 75 degree column, would be rated for 50 amps worth of current. At our actual load ampacity of 32 amps, that means that we will be loading this conductor to approximately 64% of its maximum allowable ampacity. Now, because table D3 concluded does not have a 64% column, we need to go up to the next available higher one, and therefore we use the 70% column in table D3 concluded. ACWU has a 90 degree insulation temperature rating, and therefore we use the 90 degree row, and that gives us a DCF of 1.0. Now the last step, as previously done, is to simply take all of our multipliers and apply them to our D3 value that we got based on number 8 copper. So we take our 7.7 meters, we multiply it by 2 for our voltage multiplier, again by 3 for our voltage drop multiplier, and then lastly by 1 for our DCF. And that gives us a grand total of 46.2 meters and represents the fact that we could run a maximum length of ACWU here of 46.2 meters between the panel and the load that it supplies. Now in reality, this is the base voltage drop calculation that you would do in the CEC, and there's lots of questions that are developed around this particular process, but in actuality it doesn't represent the most practical type of voltage drop calculation that we would have to do in the real world. So what we're going to do here is we're going to shift gears and start to look at voltage drop from the perspective of a much more practical calculation that you would actually do on site quite regularly. The reality is, when we're out in the field and we're now looking at feeding a load from a panel with a particular size of wire, we don't get a lot of play in terms of where we put the load or where we put the panel. In fact, typically speaking, those two things are fixed. Rather, what we are faced with usually is a scenario where we have to choose a wire size that is capable of supplying the load at the distance that it's required to be at physically without exceeding 3% voltage drop. And so in fact, a much more practical calculation is to use the voltage drop system in the CEC to determine the wire size that we would be running in order to have a circuit of a particular length carrying a particular current. Now, because this is not the way that the system is set up within the CEC, we have to kind of manipulate the system a little bit and approach it in a fairly unique way. So let's take a look at a practical problem. Here we have a 240 volt load that draws 25 amps, and we need to feed it with 46 meters of copper Tech 90 cable. And that's because the load is where the load is and the panel is where the panel is. We don't get to move those two physical entities often. And so now we have to actually just do the calculation in order to size the conductors. And the question then will come from the point of view of what is the minimum size wire that I can run and not break code in terms of the 3% maximum voltage drop that we're allowed. So here what we have to do is we have to put the data into our base calculation that we looked at the beginning of this video. So our base calculation for a voltage drop problem is focused on calculating a maximum distance that we can run. In our case now, where we're looking at it from the real world perspective, a more practical example, we already have the maximum distance. We have the 46 meters. That's the length of cable we have to actually install. We can't install anything shorter because the load is where it is and the panel is where it is. So this means now we have to look at the other values within the base calculation and determine which of these we can actually solve right off the top. When we take a look at the voltage multiplier, that we can solve right off the top because we know that we have a 240 volt circuit and table D3 is based on 120. So we would have a voltage multiplier of 2. Likewise, we can solve for the voltage drop multiplier. By code, we are allowed 3%, table D3 is based on 1%, and therefore we would have a 3 as our voltage drop multiplier. That leaves us with a D3 value and a DCF. Now the reality is that we can't calculate the DCF until we have a wire size. And in reality, the DCF is a relatively small multiplier, typically in the range of 1.08 to 0.96-ish. So it's a relatively small multiplier, whereas the D3 value, that can be a very substantial multiplier. And so we have to neglect one of these to start with, and that means that we are going to neglect the DCF. By neglecting the DCF, we now have a formula where we only have one missing value, or one unknown. And so that means we're going to eliminate the DCF for now, We'll then transpose the formula so that we isolate our unknown value, and that is the D3 value. And that D3 value then can be calculated having transposed the formula such that our 46 meter maximum distance divided by our combined multipliers of 6 gives us a number of 7.666 repeating. Now what we can do is we can actually take this number and our load ampacity of 25 amps into table D3, and we can try to locate a number that's equal to or less than this calculated value. And I say less than because this problem is always from the perspective of what's the minimum size that we can run. If we went into table D3 and we chose a number that was equal to or greater than this number that we just calculated, then in some circumstances, not very often, but in some circumstances, we would actually select a wire size that's too large using this following process. And so when we go into table D3 and we go across at 25 amps and we're looking for a number that is equal to or less than the 7.666 number that we've just calculated, then what we would actually find is a number of 6.2 in the table. And that 6.2 is going to be associated with a particular wire size, and in this case, number 10. Now what we've done is we've isolated a starting point for our calculation. We've identified that number 10 could be an option, and now we need to verify it. And the best analogy that I can use for this is around the idea of getting on target when you're zeroing a rifle. And so if we are trying to zero a rifle, we'll often bore sight it, and what that does is it just allows us to actually be on target to some degree. We may not be on the bullseye yet, but it allows us a starting point where we can now make the appropriate adjustment to end up on the bullseye on the next shot. So here what we are doing is we're identifying a number for our AWG size, number 10 AWG, and that's going to give us a starting point. Now we would go through and actually verify whether this is the appropriate wire size or whether we need to go one step higher. So let's take a look at the rest of the process. We've gone into table D3. We've taken our value of 25 amps, that's our actual load ampacity. We've gone across at 25 amps until we hit a number that's equal to or less than our actually calculated D3 value of 7.66. And of course, when I say less than, we don't go for the absolute lowest number, we go for the next closest lower number. And so what you would see in table D3 here is that in the row of 25, we have 6.2, and then the next available number is 9.9. And 9.9 is associated with number 8 AWG. So our choices when we're doing this part of the process are either to select 9.9 immediately or to select 6.2. And because we know that we've neglected the DCF up to this point, the DCF in this process may give us sufficient increase of the 6.2 number to actually get the maximum distance that we need. That's why we choose the smaller of the two options initially. Worst case scenario, when we run through the calculation having chosen number 10 initially and end up short, then we'll just upsize to the next available size and we know we'll be good. So we start at the lower of the two numbers, run the calculation using now a DCF, And then if we're still short on our maximum distance that we need, we just simply go up to the next available size. So we have chosen number 10 AWG initially. Now we need to actually verify this. And so what we do is we run the calculation with our number 10, and we take our 6.2, multiply it by the 2 that we got for a voltage multiplier, multiply that again by 3 for voltage drop, and then multiply it by a DCF. And of course we would get the DCF the same way we would get it in any other calculation. We'd base it upon our percentage loading and the insulation temperature rating of the conductor. So at 80% loading, 90 degrees C rated wire, our DCF is only 1.0. And the consequence of now running the calculation with number 10 is that we end up with a maximum distance allowable of 37.2 meters. The problem, of course, is that we need to be able to run at least 46 meters. And so what we have done here is we have proven that our number 10 is actually no good. And therefore, we are going to need to go up to the next available size, and that is our number 8. Now, let's take a look at this last little component that we've just briefly discussed. So having taken our DCF of 1.0, integrated it into the whole calculation, 6.2 multiplied by 2, multiplied by 3, and multiplied by 1.0, we come up with 37.2 meters. That's the maximum distance we can actually run a number 10 wire in order to carry this 25 amps at 240 volts for 3% voltage drop. And as already discussed, that's too little. We need to be able to go 46 meters. And so what we would do then is just simply go up to the next available size, and we would actually have to run number 8 AWG to feed this load. So now that we've got that process down, working the problem in reverse, let's take one more example. So we're going to say, what is the minimum size of TW75 copper conductors that can be pulled to feed a 120 volt load that draws 12 amps if the length of the run is measured at 45 meters? And again, this is practical, this is real world, because we don't often get to move the load closer to the panel just so that we can run a particular sized wire. Rather, the panel is mounted where it's mounted, the load has to be where it's going to be, and we now need to choose a wire size that's capable of running that distance for the voltage drop that we are permitted. So, step 1, we ignore our DCF and we solve for a hypothetical D3 value. We take our 45 meters, that's our maximum distance, and we transpose the formula, dividing that 45 by our total multiplier of 3, and get a D3 value of 15 meters. Now what I have to do is go into table D3, use that 15 meters and an appropriate level of current based on our actual load current. Our load current is 12 amps. That isn't an option in table D3, so I use 12.5 amps, and I go across that row until I get to a number that is as close as possible to 15, but lower, and therefore the number is 12.4 meters. Again, we could go with the next higher number, which would be 19.7 meters. And of course you can see from this that it would be more than enough to run number 8. We would be absolutely golden with number 8. But because these questions are always from the perspective of what is the minimum size, we should always start at the lower of the two numbers just in case our DCF is sufficient to get us the distance we need at that lower size of conductor. So we will start with number 10, and we'll take our 12.4 value and carry that forward and actually run the full calculation now, having chosen number 10. The result of that is that we take our 12.4, we multiply it by our total multiplication factor, which is 3, and then we get a DCF of 1.09 based on less than 40% loading. And even with that DCF of 1.09, we are still slightly short. We come up with a maximum distance that we would be allowed to run with number 10 of 40.548 meters, and it's close, but not close enough. And therefore, what we have to do is simply go up to the next available size, and that means that again, in this particular example, we would be running number 8 AWG in order to satisfy our maximum 3% voltage drop at 120 volts, drawing 12 amps of current. And that takes care of a voltage drop calculation from a more practical perspective, as you would have to do in the field.